straight into comparametric equations, and people usually struggle a little bit. It's simple. Comparametric equations you can convert to ordinary differential equations, and you all know how to do ODEs, so it shouldn't be that hard. But some people struggle with it a little bit at the beginning. So what I did was I just said lab 2 is going to be very, very easy. It's just assemble the lab kit and make a hello word. Take a picture. And so we've got a motor here, we've got a swim here, and you know, this works here, and there's a wheel. The lab kit has a wheel. This is a steel wheel. The lab kit has a nice rubber wheel, which even works better. This steel wheel is a little harder to use because it tends to slip a little bit. And you can just roll it along the countertop like this. And so I wrote an interesting paper about using rotary swim on linear recording. Actually, I should make sure my mic's on because the sound is.
Oh, yes.
Because we've got a remote. I think there's somebody who's away sick, so I want to make sure. By the way, if you're going to be away sick and miss a class, let me know, and I'll just make sure the sound is good and everything so that you can hear it. I think from what I was hearing from the one student who was away sick said that the sound was good. The sound turned out well, so I think that this method works good. So now. What I want everybody to do is to learn
Do you want to show the back, like how it looks like?
How this thing works. So there's a motor here on the swim. There's a breadboard, and then don't stick the swim down. The swim has peel and stick tape on it, but don't stick it down right away. We have included in each kit is a little bit of black wire like this to tie it on. So you notice how it's tied on, it's not stuck down. Once you're absolutely sure you want to do it, you can peel and stick it down with the double-sided, because it has double-sided tape on it already. But don't do that until you're absolutely sure what you want to do. Try a few configurations first. Like a lot of times what you want to try is, okay, the first thing to do is try this single-sided, try it double-sided. You might want to try flexing it and that kind of thing. So there's a few different things you can try. The breadboard goes on here. Also, the breadboard has peel and stick on it as well, but don't stick that down either, because what you want to do is put the battery in there first. And the kit does not include a battery. Batteries are expensive to ship. It's always a nuisance to ship batteries, so usually people source batteries locally. So I'm assuming that everybody either A, has a USB battery, or B, can get access to one or would use it for other things beyond this lab kit. So you know, it'll be used for this and a million other things. So I've got a USB battery that came with my Smart Swim. A lot of things come with a USB battery. The Smart Swim comes with a USB battery to charge it up. And so you take your USB battery and you put it between the breadboard. You put your battery in here and then the breadboard on top and tie that down. And what you want to do is choose a battery that's roughly the right mass to counterbalance this, and then you can move the battery outwards and inwards to get it at the right mass. And then when you're ready to get it in, you can put a little bit of double-sided tape on here. You don't want to stick it down too well because you want to be able to move it, just enough that it doesn't slide. And what I'll sometimes do is peel back a little bit of the double-sided tape on the breadboard, not too much of it, just a little bit, just enough that it kind of sticks to the battery a little bit, and then tie it on with wire so that it doesn't slide around. I put a little bit of tape on here so it doesn't slide around too much. Now, you got this, it's heavy on the bottom because there's no battery on it, but once you put the battery on there, it'll balance nicely. And then I've got a wheel here. So there's the motor here. There's 2 screws holding the motor on. You got 2 screw holes. You put 2 screws on there. By the way, they're M2.5, the screws. And I'll push the wheel on. Now the wheel's on here, so once the wheel's on here, of course I can do this. And be careful not to do this too much because it might come flying off if you don't put the set screws on. But it depends on how hard you push the shaft on or the wheel or whatever. Just be careful it doesn't fly off and hit someone or something. So now you can spin it, and of course the motor can spin it. You put a battery on it. You do all kinds of things and make your spinning display. So now, of course, once I sit this down here like this, it balances nicely. And you can do all kinds of fun art because you can spin it with translation and rotation. So you can kind of go like this and do some nice patterns in the air with long exposure photography. It's a lot of fun. So what I want to see is the hello world really simple. So you're going to put this here on a desk like this and just push it across like that. So the first part, just make the hello world work. Just make it say something. Your name is good because you want a profile picture. So the MIT admissions committee or your future employer, whoever it is, looks, hey, that's really cool. What is that? And it becomes a conversation piece. Oh, you can say, oh, well, that's the predecessor of the metaverse. That's the sequential wave imprinting machine. Extended physical metaverse, I guess you'd call it. It's where the metaverse meets the physical world. Metaverse and universe together, what people call XV, extended verses, where all the verses come together. So anyway, this is simple. You've got that on here, and you're gonna put something on here like your name. And then a good trick I find, it's nice if you're gonna see here, if you got your lab partner, rather than trying to do a selfie, the one I did and posted, that was a selfie, so it's pretty crummy because I push the camera, run the self-timer, stand next to it, and of course it looks like crap because I didn't have it orchestrated properly. I had nobody looking through the viewfinder, so I just went like this, literally. I just went, push down on the camera, run back, stand next to it, hope I got the right look and the right lighting, and bang, got a picture. And it was okay. It shows the wheel spinning around and everything, but you can do something a little bit better where you sit here like this. You slide that swim. Usually what I like to do aesthetically is put your name on there and maybe put some grat on there, put a few lights that are on constantly so you got like a pattern in the background behind. And then it'll light up your face a little bit too. It looks pretty cool when you take a picture. So one of you in any group hopefully has a non-Apple phone, because when you have an iPhone, you're inside the iJail. But if you have an Android, you can usually put manual settings on the exposure. So my S21 will only go up to 30 seconds, but the new Samsung will do up to 2 minutes long exposure. So hopefully if you've got at least one member has something that isn't an iPhone. If you have an iPhone, you have to download an app to get long exposures. So it's a bit inconvenient, but if you have something that isn't an iPhone, usually you can the camera itself will just give you long exposures. Or if you have a real camera, that's even better. But a lot of people don't actually have real cameras anymore because they do everything with the camera phone. But you put your camera on an exposure, like maybe 5 seconds or something like that, however long it takes to roll this along. So now for the very basic part, like you can do quite well in the lab if you just say something with the LEDs. That's kind of what I want to see. I want everybody to understand, what is this thing? I don't expect you to calibrate it. I don't expect any ordinary differential equations or comparametric equations or anything. Dead simple, just say something, say your name or whatever, because that is just an introduction to how to use this as a measuring instrument, as a test instrument, as a calibrator, as a camera calibrator, as an artistic tool. By the way, for art, we're getting together for Nuit Blanche on Saturday, so tomorrow. So join us. Let me know if you want to be part of that, and we'll meet up tomorrow and finish it. I think the goal is to get the application submitted tomorrow. Get it all written and submitted tomorrow. And then Sunday I'm going to go for a swim and relax and chill. If for some reason we don't quite get it done, we can always drag it a little bit of Sunday, but I sort of would rather go for a swim and not have that thing hanging over my head. So we're meeting, actually there's a New York Times article being written on this, and there's the New York photographer from the New York Times will be there, so it'll be a good photo op. Photo OP, where OP stands for Ontario Place. Photo op means a photo at Ontario Place. And so I have the New York Times photographer, so if anyone wants to come out and just run along, dip in the lake or whatever, feel free to join us for a fun little splash and make a little splash. And we're trying to raise awareness for the importance of clean rivers and lakes and waterways and access to water and all those sorts of things for physical, affective, mental health. So now, when you do this, right now we're looking at, yep?
You could mention to bring the lab one for next week.
Yes, that's another thing too, is that what I'm expecting is that you'll bring your cameras. Now, if you've got a big camera and you can't bring it, obviously, so be it. But at least bring what you can, because what I want is a showcase next lab. At the beginning of lab 2, you're going to want to bring 2 things. One is you're going to want to bring your pinhole camera from first lab, and the other is going to bring the lab kit. And so your pinhole camera, I want to do a showcase, I want to evaluate it. I'll give some bonus marks if you've got a really nice build, you know, if you've got something that, wow, like if you've got a little turret with a clicker that you can select different apertures or something like that, I'm going to look at that and say, well, you know what, that actually might deserve some extra marks. So bring it along. And so I'll grade based on the instructable submitted plus the showing of the build itself. Because you've had a chance we've shown you all how to build it, you've had a chance to refine it. Hopefully you have something that looks really cool, it's fun, works well, and it's a good example, and you can do a little showcase at the very beginning of Lab 2, Showcase Lab 1. So now, what we want to see, this is a scientific and artistic machine, sequential wave and printing machine, and you wave it back and forth and it imprints text and graphics. So the very, very most rudimentary form is to just put, let's say you want to put hello world on here. Let's say you want to say something, or your name. You're going to put something on there, and let me just say an example here.
One more thing to mention, the training.
Yeah, we've also,
MyFab training.
There's an online MyHull training. There's online safety training. So don't forget to do the online safety training. So
One of these, we're going to MyFab from now on.
So we'll have a little bit of soldering station set up there and everything. So now, let's suppose that...
You can put it here, like on top. On top of this.
You can put it on here, yeah? Maybe it'll stay on, maybe you can hold it there. Maybe it'll sort of stay on. It won't stay on, you're gonna have to hold it if it's up there.
I got it.
Okay. So now we've got this, actually that's not gonna work.
I want to get it higher, but...
Yeah, but I got to be able to write on it too, so. We could just move to the other end too and come back. You guys want to just change to the, whatever. Let me know if you can't see this and we'll move it to the big chalkboard. So the swim, you want to light up, say you want to say hello. So let's say I was doing this with 7 lights. Bit less than a byte. 1, 2, 3, 4, 5, 6, 7. So to say hello world, you're going to light all of the lights first, turn them all on, and then turn them all off. And then you're going to want to turn on the middle light only, and keep the middle light on. 1, 2, 3, 4. And you could make it 5 by 7 or infinity by 7, because you could just leave it on. And then it would look like an IBM logo, you know. And then at the end, you turn them over here, you turn them all on again. So that's the letter H. And you can see you can break these letters down into just ons and offs, right? So if you look at SWIM, sequential wave and printing machine, you can see that. Now, sequential wave and printing machine plots images, text, graphs, graphics, plots, functions. And when it's plotting text, you can also use fonts. You can do this manually, turn it on, or you can use a font library. And there's lots of font libraries around that you can look up and get running. So this will be really easy. This is something you can do without much effort at all. Just put the processor on there, hook it up, send some text to it, put a nice graph on there. Like if I'm putting a certain color of text, you could also put a nice background on there perhaps so that it produces some background light or has context. So the graticule or reticule is the context. So you'll notice here when I'm plotting this function, just so that it has space or presence in space. See, that's a sine wave, but what you'll notice is that some of those lights stay on all the time at a very dim setting. So it's a bright sine wave superimposed on top of what's called a graticule or a reticle, or grat for short. So the grat here consists of 7 faint lines, and then the sine wave is a bright sine wave on top of those 7 faint lines. This was done with 35 electric lights in 1974 on a strip. I invented, designed, built the world's first addressable light strip to make this sequential wave imprinting machine. What I realized when I wave it through space is it wants to have presence. You want to be able to find yourself in space. So I put these little lines on here. And originally I put 5 lines on, and then I put stuff on it, but people thought that looks kind of like music, because music usually has 5 lines on it. So if it is music, then I'll use 5 lines, but if it's something else, I put like a different number, like 7, so it doesn't get confused with music. And if I make that a little smaller, you can see it there. So you can see here, there's a sine wave there, roughly. This is actually a received signal, and that's a radio wave being received. Here's a little thing that shows the build of a SWIM. Put the chips on a breadboard, drop it on, but you don't have to do that. You're just going to use the microcontroller. It's actually quite easy. You don't need all that work. Here's the SWIM in the National Gallery in Ottawa, world's first wearable computer, and it's a row of lights, and so on here. There it is with the GRAT, 7 lines GRAT. And you can kind of get the idea there. And if you look here on new SWIM, you can see some newer examples of SWIM. And then, so you can, gives you an idea, you can get an idea. There's Jeffrey Hinton and I doing the sequential wave printing machine. So you can see there, Jeffrey's holding a smartphone there, and I'm swimming it out. So you can see the waveform there. And so it'll give you an idea. Now, if you hunt around, you'll be able to find all kinds of font stuff around here. Like if you go to wherecam.org ece385, which is a 3rd-year course I teach, I did the SWIM there. Lab 1, I did this whole thing here with the sequential wave and printing machine, and there's fonts here. Search for lecture on fonts. I gave a brief lesson on fonts. You don't need to know this, but if you want to, you can find it. And bitmap distribution font. Here's how fonts are stored. You can look in there, and you can see there's basically the font letters. I cropped off the unnecessary material and reduced that down and made it a little bit simpler. And then there it is here.
Sorry.
And then
The screen is too large, you have to make it smaller.
or too small, I have to make it larger,
No,
maybe.
the text are not showing up on the left, like the TV's not showing.
See, with analog, everything's perfect, but with digital, it's only approximate.
That's better.
Analog is exact.
Yeah, that's good.
Digital is just off by a little bit. There we go. Now now my window's way over on my screen. Okay, so anyway, there it is. And I wrote a little octave script that converts. I invented something called BTF, Bitmap Teaching Font. And I made a little octave script that converts bitmap, like a BDF standard font, into BTF, which is Bitmap Teaching Font. And that'll show you how it allows you to see the font. And BTF, I just made the fonts look like they are. So it's very space inefficient, but you can see all these fonts in here. So there's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, equals, question mark, all these different things. There's the letter A, B, C, D. So there's the letters there's your H, in BTF, Bitmap Teaching Font, which I made. So if you wish, you can take a look at that. You don't have to. You can just wing it. Just put your name on there somehow. You could even just do it as an image if you've got a Chinese character. Like if your name is whatever, you can put it. Sometimes it's good. I don't know. Like if your name is Tian, I don't know if that's field or sky. So sometimes it's better to write it in Chinese because then you can tell which it is, right? You know, that's a good example. You could do that if your name is Tien, then you know, write it like this or like this, you know, depending on whether you mean field or sky. And that's what you could do that as an image. You could just program those symbols and make it appear, or you could program it as an image and read the image array out. And so I want to see something like that. It'll be fun anyway. I think Lab 2 is going to be a lot of fun. So the first simplest way to do it is you just light up the letters. So this is the letter H. It's a little bold-faced, a little bit stronger. It could just be one bar and then across in another bar. Depends on how dense you want the font to be. You've got 72 lights if you split this in half, so you can actually have quite a nice well-formed character. And you basically, you're going to light that up and then change it and change it. Now, one way to do it is just to have it go at a certain speed and adjust the speed. Speed it up or slow it down until it's right, and move this at a steady speed through space. Just take this thing, take this stick, and move it at a steady speed through space. You got to hold still here. You go like that and move it at a steady speed, maybe at arm's length like this. And that'll work pretty good as long as you move at a steady speed. If you speed up or slow down, the letter will be compressed at one end or expanded at the other. So that's one way to do it. In the original Swim, I put a radar set in there that clocks the data through. So it uses the wave, the phase, which is the arctan of the imaginary divided by the real. It uses the phase to push through the sequence of letters. So I had it so every degree of advancement of the radar wave resulted in moving to the next column of the array, let's say, or every certain number of degrees. So that will work. I'm not expecting anything that sophisticated. So your first step is just do it at a constant rate and try and move it at a constant rate. And then the next step you're going to do is you're going to put the wheel on here, and you've got an analog input from this motor. The motor functions as a generator. When you turn this wheel, it generates electricity, and then you sense that electricity, and you can tell how far along you are based on the waveform of this. So that will get you thinking about motors, because you know you're going to sense that waveform and move through space with that waveform. So that will be your very simple task, is then to put that on here and roll it along. So that's what I'm hoping to see for Lab 2. So now these are some prototypes. These are a couple of prototypes of the Lab 2 piece. So there's this piece. You can see this is fixed width, and then I thought, well, it would be nice to have this end a little bit fatter. And so what we did is we just took a little bit off of this end and put it down here. You can see how if these are stacked alternately, they are space efficient. And then finally, this is the design, which is slightly wasting a little bit of material because they don't quite nestle, but that keeps the thing the same width all the way down to the end. So it's kind of a trade-off of space efficiency versus material use versus how this fits, and they're alternating when they come out. So now you can see one interesting observation that I found of these is they're not as stiff. So this is the original. I put these two together. This is this is the original. Can you see that
It's due to laser cutting.
It's not due to the laser cutting. Who else wants to hypothesize why this one flops around and that one's really stiff? Yep.
Is it because of the grain of the wood?
Yes. The scraps they gave me from the Myhall Center had the grain running lengthwise. And when they cut this for me, the grain was going the other way. So that's something to realize, is that the grain can be in various directions. I don't know if this is really important. I better. Yeah, just leave it between the two front doors. Thank you.
Yeah, thank you.
Yeah, that's our motors for the, we ordered some motors to experiment with. So I'm ordering various motors to play around with. So this motor that you got here is 12 volts, and that will give you a good strong signal. when used as a generator. So when you're going to use a motor as a generator, it's better if it's a higher voltage because it'll give you more signal. And the A to D converter is relatively sensitive. It's 12 bits and you only need, you know, there's 72 LEDs. If you had like 128 LEDs, you'd only need 7 bits. And you got 12, so you have 5 extra bits, so you can have a gain of 32 times. So it's not too bad with a 12-volt motor. You can move it fairly slow and still pick up the signal. But yeah, the grain is going the other way. So I asked them to rerun it with the grain going this way, because some pieces, these pieces are 18 by 24 inches, 1 cubit by 2 feet. And they are sometimes going grain long ways, sometimes going grain width ways. So I'll pass these around because this is an example of how something can bite you in the tail when you don't expect it. You can see if, as I wave these up and down, I've got them held together like this. One of them flops around a lot more than the other. And in fact, this one is pretty flexible. But then that I got thinking that might be in this case, we want it to be stiff. We probably want to rerun it stiff. But there are other situations where we'd like this to be flexible. And this is actually quite nice for some things. For this, we want it to be stiff, but I'll tell you where flexible makes sense. So years ago, back in the 1970s, what I used to do is take these swims and use them to draw patterns through the space, waves, print waves. But I also use them as a light source to light up somebody's face or whatever. So let's say you're here and you kind of want to play at the boundary of art and science. You want to swim something out, like eventually you're going to plot graphs and functions and patterns and phenomenology. But for now, you're just saying your name in lights. You're going to come over here. Now, if you're wearing eyeglasses, you want to see your name in the eyeglasses. So you might go like this. You might take your swim like this, swim it out, turn it around so the camera can't see it anymore, bring it right across your face, nice and close like that, and swim out your face so your face looks kind of swimmy as well. And then that's kind of nice too, especially if you're wearing eyeglasses, because you'll see your name on top of your eyeglasses. One single exposure photograph. And you can, with a bit of practice, you can do it one single motion, right? You go down like this, turn it around, and all in one go, 5-second exposure, 1001, 1002, 1003, 1004, 1005, say, done. And then you've got this really beautiful picture, but it doesn't quite wrap around your face. It's better to be close to the face. So what I've got here is I used to, back in the 70s when I made these swims, I made some that were curved so I could light people up. So I had one that was curved around the face, one that was about curved for the body, and get one that's curved a little tighter for the arms. And so a swim like this is a curved swim. I'll pass this around so everybody can see it. But this, you can light up your face like this and the swim comes in nice and close, sort of wraps around the face with light, which visually, artistically is kind of nice. I'll just plug this into a USB battery here, Uzix Smart Swim battery. And so now this is just producing a nice pattern. So you can imagine during a long exposure photograph, this will make a nice pattern. Now, this is cut out of cardboard, but back to my point about this mistake with the laser cutter is actually what was first a mistake turns out as an opportunity. You should always see errors and omissions as opportunities, because now I could print 1/2-inch strips like this, and I could bend that, put that on another piece of laser cut in an arc like this, and actually make a curved swim, which might be nice to light up somebody's face or to capture some phenomenology that's curved in space. Again, you can even spin that around and make something 3-dimensional. There's lots of cool things you could make with this material now that we know it's flexible and we can bend it in different shapes. So I'll pass this around, I'll pass this around for inspiration. Try to think, what can I do with super floppy, sloppy, loosey-goosey, bendy pieces of wood like this. I'll pass these around, and I'll pass around the original stiff ones that are long grain, so you can see long grain versus short grain, and start to think about what you could possibly do creatively. What's the difference between long grain and short grain? So I think everybody knows how to do swim now, or will soon. Let's punch a wave and printing machine. That's warecam.org/ece385 if you want to look a little bit in history, some of the other course that I taught. I went into a lot of detail. I taught the students how to write device drivers, how to build new hardware, how to write device drivers, like how to extend the operating system to use the new hardware. So it was a fun course. I'm not going to go to that level of detail computationally. This is not a course on computer organization. But you can delve into here and see a little bit of the fun that we had there. But I'll go back to warecam.org/swim. Actually, if you go to warecam.org/swimvention, there's a little bit about the invention of swim. This is something artistically, visually. There's your hello world. There's different patterns and swims. And I mean, this is the basic idea here. You've got a character formation, the swim stick. Initially, all the lights are off at this point here. Next, 1, 2, 3, 4, 5, the bottom 5 lights turn on, and then they all turn off except the 4th and 6th light, and then they all turn off except the 4th and 7th light, and so on. And you can see the letter A is formed there as that swim stick moves through space. So this allows us to label the axes, something my high school teacher always said, when you make a plot, label the axes. So we can put tick marks on the axis, we can label the axis. And so initially I just want you to understand the artistic and fun and playful elements of it, but then you'll start to realize that the swim is a very important and useful tool for serious scientific exploration, which you can do by labeling axis. You can do plots, graphs, functions, and so on. So that gives you an idea. So here is a very simple hello world in green LEDs. His name's Dan, so I spelled out his name in lights there with the swim. I don't know if you can see that or not. This was January 12th, 2000. I guess that was about 24 years ago, maybe. So you can see I wrote Dan there, and then I just swim patterns all over the place. I just filled the whole room with swim patterns, fun, interesting swim patterns, and I lit him up with swims as well, too. So it's like a swim portrait, where the swim is used as a tool both for illumination as well as for directly indicating phenomenology to the camera. So it's embedded in the verses, like it's natural photography. It's just a picture, a photograph. But it bears a lot of similarities and predecessors of the metaverse and metavision. This is hello. So I just said this is just teaching the students how to say hello with 8 LEDs and a breadboard. We don't even really have to do that now because we got the microprocessor. So you've just got to stick the microprocessor on the breadboard, hook it up to the 72 LEDs. You can turn them all on and off at will. Whatever pattern you want to put on there, you can say whatever you want to say, and just have a little bit of fun with it. The idea of Lab 2 is to have a little bit of fun. And so what I want to see is I want to see bring in Lab 2. If you bring the lab kit on Tuesday and Wednesday, I'll help you get going on it as well. And then when you come in on Thursday with your camera, pinhole camera, and the lab kit, try to have the lab kit saying something like, try to have your name on there, and I'll take some pictures for you. I'll help you. I'll show you how to do photography, I'll show you how to set the camera. We'll try to use your camera phone. I'll show you how to do it with my camera phone. We'll get a couple of nice pictures. So what I'll try and do is help everybody get a really good profile picture. So Thursday will be like a little bit of a tutorial where hopefully you'll end up walking out of the lab here with a really great profile picture for LinkedIn or Facebook or Instagram or all these social media where you can have a really cool shot that shows you leaping out of the metaverse and beyond physical metaverse. So this is, hello world, very simple. That's 2005. Remember, I've been teaching this since, I guess, the 1970s, so we've had quite a few years. Quite a few people have learned how to make addressable strips. Now you can buy addressable strips, but bear in mind, originally I had to invent, design, and build the addressable LED strip as a concept, but now they're readily available. You can get them on DigiKey. You could order it on DigiKey and have it here tomorrow. Like here, obviously, you can just buy the lab kit as well. You can get all these parts just about anywhere. You can get them at Home Hardware, Creatron, DigiKey. You can buy them just about anywhere. So the lab kit, we've just kind of created a simple lab kit. A little bit of subsidization going on there, so the lab kit will cost a little bit less than what if you ordered it at DigiKey and so on. So we're trying to help out. We're throwing in a lot of the parts are just being donated into the lab kits. So hello, fellow students of ece5162024jan19. So that you can put a nice message there and swing it around. What's missing from that shot? In terms of my artistic sensibilities. Yeah? Yeah, there's no grat. So I like to see a grat because it gives you spatialization, it gives you context, so you know where this thing is. When you take a photograph of an oscilloscope in a dark room, normally an oscilloscope will have a grat knob, a brightness knob to adjust the grat. So usually the grat is a traditional oscillograph will have the CRT in green usually, and then there'll be a little piece of acrylic over the front of it with a graph on it, and that's your grat. And there's a little knob that says graticule, and often the on-off control of the oscilloscope is the grat brightness. So when you turn the oscilloscope on, it goes click, and then your grat brightness turns up from there. And so if you turn your grat to 0, a lot of people go gratless. A lot of people even take the grat rate off so you can see it, but sometimes you want to put it on, and you can adjust the brightness. Most grats, you can turn them upright, they're white. There's a little light bulb in there, and if you turn it upside down, there's 2 notches on the grat that go around the light bulb, and it lights up the whole inside of that piece of acrylic so you can see it. And when you put it one way, it's white, and if you turn it around and put it upside down, it's red, because there's a little red filter over the part of it that touches the bulb. So usually you can have a red grat or a white grat. But now, of course, you can make the grat any color you want. But a grat helps provide context. So I'd almost make the fonts a little smaller. For example, sometimes what I would do is I would make my font not go all the way to the edges, and then I'd have the top and bottom pixel on just a little bit so that there's a ribbon of light. Or you might have just a little bit of glow behind it or something. And you can experiment with different grats because it gives you spatialization. If you're plotting a function here, it gives you the ability to see how that function moves through space. Hello world. This is the really classic thing, is just saying hello world. And so you can see that here. I've got the M file. I've got all kinds of links. You'll find, there's my fonts there. I made a little, it's an Octave. I use Octave, but who here, anyone here use Octave? Anybody here is MATLAB? Just about everybody. Well, MATLAB is closed source, but Octave is very similar. It's the same, pretty much very similar. I switched from MATLAB to Octave some years ago. The main difference is with MATLAB, when you do C4 files externally, it's CMAX. There's something called CMAX and FMAX, which is to write foreign file library interface. So if you want, usually you write C code for the stuff that has to run really fast, and then you use MATLAB. And what I would do is I wrote the CMAX files for the inner loop part that has to run really quickly, and then connect those to MATLAB. But with Octave, you just use GCC. All your external libraries, everything you want to pull in from C is just GCC, or the Fortran compiler, the GNU Fortran compiler, or the GNU C compiler will work nicely instead of CMAX and FMAX. But if I go Octave --no GUI, there's Octave. And then so I can go, for example, T equals 0 to 1023, format compact. That'll just save space. That's T, tightens it up a little bit. And then if I go T equals T over 1024, So it goes almost 0 to 1, and plot, or g, the function, say, equals cos 2 times pi times t times, say, 5 cycles or something like that. And plot g. So if you've used MATLAB before, you probably recognize what's going on here. It's pretty easy. So you might want to learn some Octave because it's easy, free open source. I try to do everything free open source whenever possible. The other program you're going to want to learn is Inkscape. That's what My Whole Center uses. I'm so glad that the My Whole Center is coming around on the ethical side of free open source, but Inkscape is the way it is. I think it was 009. There it is. Inkscape, SwimStick 009. There's the file from yesterday. I just printed that out. I made the changes. The laser cutter could not go right to the edge, so I cropped it. And you can see here, it doesn't quite go to the edge, so you have to break it apart, which is fine because it's almost to the edge and then it just breaks apart quite easily. And so there it is. Black represents burning. Don't be confused by the terms they use, raster and cutting and etching. There's a lot of confusing terms, but really it's all vector graphics. All of it is vector. There's no raster graphics happening here, even though they call it raster, perhaps incorrectly. The black means to burn the wood. The blue means to cut into the wood, and the red means to cut through the wood. So you're going to burn, etch, or cut. And so you can put this burn sequential and printing machine text onto there, and that'll show up once the swim is on there. And on the other side, there's a ruler calibrated in units of, I call it a NES, let's say it's the spacing between the lights, these blue tick marks. So I've created a new unit of measure. So 42 NES is 29 centimeters. So you know how we've calibrated that. So that a NES is the spacing between the LEDs. So it's nice to introduce new units of measure, either humorously or for practical purposes, like Smoots was introduced humorously, but NES maybe is a matter of practicality. So you can figure out exactly how many centimeters is equal to 1 NES, and then you can count it in NESs. So I've got a tick mark every 6 NESs, because 72 is a highly composite number, so we don't have to use base 9 plus 1. By the way, every number system is base 10 in its own base. So if I'm thinking binary, then binary is base 10. 0, 1, 10, 11, 100, 101, 110, 111, 1,000. So I'm just counting in binary. If I'm thinking in binary, somebody's asking, what base is that? Well, I'm going to say it's base 10 because I'm think binary. And if I can think of another base that's also base 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, 10. That's base 10 in its own base. So I like to instead talk about the crown of something, the one less than the base. So I'll say crown 9. That means, or base 9 plus 1, or base F plus 1, or base 1 plus 1. Because I can't say base 2 because 2 doesn't exist if you're thinking binary. I could say base A. When you go to Lucky Moose to buy groceries, it's all done in base A. But of course, then they're going to look at you strange because they don't have that number in their base. So I'll wrap up here by saying I've made a ruler here. So the ruler is in units that are not millimeters or inches. It's not imperial and it's not metric either. It's a new unit of measure. So be comfortable in any units, whatever works best. So the strip is 24 inches long. It's an inch wide, and it's marked off in these NESs. So if you can think in different units, it makes life easier. And the base, there's 72 units. So we might as well think in terms of NESs in groups of 6 and 12. So I've grouped the tick marks in groups of 6 and 12. So if you want to measure something, you can use this ruler. You've got a ruler built right into this. So you can measure your own face in NESs and know how many tick marks are going to be on there. Start to think scientifically and creatively. So I could measure, I could say my name is Steve Mann. So if I might just put Steve, let's say, or I might even put my last name as a single letter in the Old English alphabet. So in Old English alphabet, I would probably, just for simplicity, you can shorten your name. You can pick a symbol that best describes you. I would probably use this symbol, because that's a single letter in the Old English alphabet, which is my last name, Man. Or Steve is short enough, or if you have a nice short 3-letter name like Dan or something, that's even easier. And you put that in there, and then you can measure about how long it should be. So you know how many nesses high your name's going to be, right? So if you want a grat, you're going to want to reserve some space for the grat. So maybe you'll make it 60 letters high. So 60 nesses high, 60 pixels high. So you'll have 60 nesses for the height. So now you want to measure how far along and plan it out. So I would take on my table and mark it with chalk or with masking tape or something, and measure how many nesses across the aspect ratio of the letter. Letter might be 5 by 7, right? So maybe it's 5 units wide and 7 high. So, or it's 60 by something. You might say, it's okay, my font, I want to make it 60 by 42. So then what you want to do is measure 42 nesses and then figure out how much space you want between the letters. Do you want to go proportional, or do you want to go fixed spacing? So like the letter I, do you want to make it closer for the letter I, less spacing because it's a narrower letter? You got to decide that, and how much delay you want. And so you could mark your table off and say, okay, that's how many nesses. That's the S in Steve. The T is going to go from here to here. The E is going to go from here to here, and so on. And then figure it out. You might have capital letters. You might start your name with a capital, which will be a little bigger, and then lowercase letters might be a little smaller. You might allow for letters to hang down. If your name has letters that drop down below the line, like if it has a Y or a G or something in it, you got to allow space for that. So you got to start up here with the other letter. It might have, so figure out what you want to put on there, plan it out, mark it off, and then you can measure it in nesses along the table, and you can tick it off in units of nesses. That way you don't have to convert to centimeters inefficiently. Just try to think in nesses. People used to say think metric, but I think in whatever makes the most sense for the job at hand. If you're doing the piece of wood that's 24 by 18 inches, think in inches or feet. Don't think metric for that, because it doesn't make sense to try to think metric in a world that isn't. So whatever it is, think nesses. And so now measure it all out in nesses, plan it all out, execute it well. And then when you come here on Tuesday, I can help you get going. Come here on Wednesday. We'll probably do Wednesday in my hall. Hope you get the online safety training done by then. And then the Thursday, I'll do your portraits for you. But by Thursday, I want you to have it all figured out so you know exactly what you're going to do. So you're going to sit here, you're going to roll that along. Hopefully you'll have some pictures already, which might not be picture perfect. I'll help show you how to do professional shots, because I've done a lot of magazine covers. I've done a lot of professional photography stuff where I've photographed people all over the world at a level and caliber that's suitable for magazine covers and stuff like that. So I'll show you how to do that. I'll show you how to get some really nice professional quality pictures. So it'll be a fun learning experience. Good.